Thanks all for coming today. What I'd like to talk to you about is my project, which was on enabling multi-scale simulations of complex fluids, especially in confinement. And this has been a project done in collaboration with my advisor, Thanos Panagotopoulos, and also Rosh Nico-Boschman from the University of Mainz in Germany. And so I'd like to start, as any good place, by defining what exactly I mean by a complex fluid. And so complex fluids are kind of the thing that drives our products and the things that we see around us and are also inside us every day. So there are things like consumer products, like shampoos or shaving cream, paints. They're in biological materials like blood or membranes, and also in industrial processing, so extrusion molding of plastics or in any of the petrochemical industry. And what's a defining characteristic of these complex fluids that differentiates them from a simple Newtonian fluid like water is that they respond to their flow conditions in terms of their macroscopic properties. So one example is a cornstarch water mixture, which you might have seen on YouTube or something, where it looks like a liquid, and if you press slowly on it, you'll sink into it. But if you run really fast on it, then you can actually walk on water. And the origin of this is the underlying microscopic structure of the fluid and the things that are in it. And it's a really highly non-trivial problem that many of these companies sink tons of R&D dollars into to figure out what's the right formulation for their product. And so as one motivating industrial example is enhanced oil recovery, where after a well we've already gotten all the easy oil out of a well, then there's a third stage of oil recovery where we inject a chemical mixture that can have things like surfactants, which is soap-like and helps pull the oil into the water phase, polymers, which serve as viscosity modifiers, and also nanoparticles that can help agitate the mixture in the formation. And the big question in these cases is, what exactly is the best formulation? And also, what are the fundamental physical effects that make something more effective than the other and gives you the properties that you want? And the design space for this is huge because of the different chemistries that are possible and also the different concentrations and compositions that you could imagine. And so computer simulations are a very effective tool to allow us to rapidly explore this design space. And so if we wanted to choose the type of simulation that we wanted to do, we just heard about molecular dynamics and atomistic models. And that occupies this great range of very high resolution models that are done on small length scales and shorter time scales. But unfortunately, that might not span the relevant process time and length scales. At the other end of the spectrum, we have things like constitutive models for CFD. And these are very good at accessing these large scales. But unfortunately, they by necessity have to smear out some of the detail that was in the underlying microscopic structure. And it's not always obvious how exactly the microscopic structure affects the macroscopic behavior and what are the properties that it's very important to capture. And so bridging between these two classes in terms of resolution and both speeds is this broad class of methods of coarse-grained and mesoscale methods, where we try to strip out some of the resolution of the atomistic model, but retain the important details. We can do simulations there, determine what matters, and then feed them up into a higher continuum description. And so in a typical atomistic model like we had from MD, if we had a polymer embedded in a solvent, the polymer has some degrees of freedom and interactions that are fairly easy to treat if it's in a dilute solution, and it's surrounded in this bath of solvent. And the solvent is unfortunately the very expensive part of the simulation because there's lots of it. It interacts mostly via pair forces, which are very expensive to compute in molecular dynamics. And most of what it does is set the dynamics and structure of the polymer. And so if we want to accelerate the simulations, the most likely candidate to step up to this next length scale is to strip out the solvent, but retain its effects on the dynamics. And so you might have heard of implicit solvent simulations in some of the other talks. And implicit solvent is a very simplistic description of the dynamics effects of the solvent, and that doesn't include hydrodynamics. But in a lot of the problems that we're interested in, hydrodynamics are very important. And so one very good mesoscale method for coarse graining out the solvent while retaining its hydrodynamics is the multiparticle collision dynamics method. It's a bit like, if you're familiar with lattice-Boltzmann, it's like lattice-Boltzmann, but minus the lattice. And so it adopts a point particle description of the solvent. And so solvent particles simply have two types of operations. They have ballistic streaming, where they just propagate like delta x is v delta t. And then periodically, they undergo these multi-particle collisions with each other, where we artificially drop down a cell onto the point particles, and we perform some operation on them that imparts the correlations that give us hydrodynamic interactions. So the most common one, called stochastic rotation dynamics, you compute the average velocity of particles within a cell. Then you draw a random rotation vector, and you rotate everyone's velocities relative to the mean. And it turns out that because these collisions are momentum and energy conserving, that there's two really nice effects. One is that an H-theorem exists, and so we recover the correct thermal distribution of velocities as they evolve forward in time. And that also that the Navier-Stokes momentum balance is satisfied. And so we're able to do flow simulations, and we can get parabolic flow if you put it in a channel, or you can get flow instabilities over objects, all within this particle-based framework that's fairly straightforward to treat and is very stable. A great advantage of MPCD over something like lattice-Boltzmann is that it's also very easy to couple solute into the algorithm. So polymers can be trivially embedded during the collision step by treating their beads as if they were MPCD particles. And so we perform MD operations just on the polymer as if there were no solvent there. And then periodically, everybody collides together. And so we can get, so for example, Zim polymer dynamics, which is a good model for a polymer in dilute solution. And we can also couple in rigid objects. I mentioned boundaries, but we can also put in things like nanoparticles during the streaming step. And so the solvent particles will come, and they'll strike off of these rigid surfaces, and we can give no slip boundary conditions there. And the collision between the solvent and the solute imparts a torque and a force, which give rise to the right rotational and translational diffusion coefficients. And so this is an example of a type of simulation we were able to do using this algorithm, where we have a mixture of colloids and polymers starting in rest. Not drawn here are a wall up here and a wall down here, and we're going to drive flow from left to right in the movie. So the red is the big red spheres are nanoparticles, and then the polymers are just colored so you can kind of follow them in the movie. They're all the same. Nope. If I can get my mouse there. And so you can see as the simulation goes, we get this interesting effect for the polymers, which we would expect where they're stretched out by the flow due to the shear rate in the simulations. And also we observe the migration of the colloids into the center of the channel, which is a very interesting focusing effect that we were interested in for particle sorting or cell sorting. And so why do we need blue waters to do simulations like this? Typically, MPCD simulations require many particles, even though they have very simple interactions that I've already described. So typically, within this multi-particle collision cell, we have about 10 particles. And then there's anywhere between like 100 cubed or 400 cubed cells, requiring 60 to 10 or up to 640 million particles, which is a lot to deal with. Fortunately, MPCD readily lends itself to parallelization because of its particle and cell-based nature, both on the level of something like an accelerator, like a GPU within a node, and also by domain decomposition to many nodes. And so as part of what my fellowship focused on was implementing this algorithm at massively parallel scale. And we chose to do that using GPUs because of, in our experience with molecular dynamics, GPUs could give you as much as an order of magnitude increase compared to the CPU code. And so we thought this was a very promising candidate. And Blue Waters is currently, as far as I know, the only NSF-funded system that's giving us access to GPU resources at the massive scales that we really need to test these codes. So I'll give you a few details about our implementation and some CUDA-specific things that might be helpful for your projects going forward. So we chose to implement the code in the HUMDI Blue simulation package for two reasons. One, the design philosophy of the code is very GPU-centric. And so it's been written from the ground up, where the CPU is actually just feeding work into the GPU. And so we're using the GPU as almost its own processor. And so we can get really great performance by doing that compared to just offloading work. And the other is that it has a very flexible user interface. It has a Python user interface written over a C++ CUDA library. And so it lets us do things like easily swap in and out different MPCD collision rules, couple this to molecular dynamics simulations, and do analysis online during the simulations. And HUMDI Blue is available open source and to run on Blue Waters. And I think it's also part of the BWPy package, and can be downloaded there. So the cell list, where we compute who's in which bin, is the most important part of the MPCD algorithm. And so there are lots of different ways on the GPU you can construct a cell list, but the one that we found to be most efficient is to bin particles and then use atomic operations to write the particles into a cell list, which we've done in an overallocated fashion so that we don't get too many collisions on the atomic operations. So we allocate memory so that any cell is capable of holding the maximum number of particles in any cell. And in the event that we would overflow that, we just count how many go into the cell and then recompute the cell list. That only happens a few times at the beginning of the simulation. And so because a lot of the particles end up using shared memory atomic operations, it's pretty fast. We end up getting about a 3 times memory waste from this overallocation, but that's not really the part that kills us in the algorithm, and so we're OK with that. We also get good performance because our algorithm is so cell list centric from reorganizing data into cell list order. And we do this on the GPU with a stream compaction operation. So we delete basically all of the holes from the cell list, compact the data down, shuffle the particle data, and renumber them. And we can do this using, since this is written in CUDA, there's a very nice library called cub, which can be used to speed a lot of these calculations up without having to write them yourself. So we are limited somewhat by our memory constraints in a GPU. So on Blue Waters, a K20 has 6 gigs of memory. And so we need to be able to scale out to multiple GPUs. So we adopt a domain decomposition strategy, and that was supported by HUMD already, where we have non-uniform boundaries. And so schematically, the black box here is the simulation box. The red are the domain boundaries. MPCD has one technical challenge that particles get randomly shifted by half a cell to remove this artificial grid that we've dropped down. And so for our domain decomposition, we check which cells a particle could end up in where it's shifted by this half a cell, and that becomes all the cells that your cell list needs to cover. And then we have basically a safe domain inside it that is what belongs to that MPCD domain. And then we migrate particles between domains every time that we compute the cell list. And then if we want to compute something like the average velocity in these overlapping cells, then we do need to do communication between them. We pack all of our MPI buffers directly on the GPU so that there's no host device copy, and we keep things scalable. We have found that on other machines that you can get some very good performance boosts from using CUDA-aware MPI when you have GPU direct RDMA hardware. Unfortunately, that's not fully supported on the XK nodes that we have, so we haven't been able to use that on Blue Waters, but we've gotten about 15% on other machines from doing that. We also have done a few CUDA optimizations to improve parallelism in our algorithm. So when you go to compute the average velocity in a cell or something like that, you do need to basically loop through all the particles that are in a cell, which is not very parallel. And so we overcome this by using multiple threads to process a cell. And so if this were the particles that were in a cell, multiple threads access the data in a strided manner. They do some operation on it. Here I've just counted how many there are. And then we can use a warp reduction strategy using shuffle instructions in CUDA, which allows threads within a warp to read each other's registers. And so this is a very efficient way to compact the data and to reduce the data and allow only one thread to write out. Now, there is one thing that's especially important for strong scaling performance, which is that the optimum number of threads that operate on a cell, and also the number of threads within a CUDA thread block, is very dependent on both the architecture of the GPU and also on the problem size that's being considered. And so, for example, on Blue Waters on the K20X for one of our benchmarks, the optimum block size for doing the cell averaging was 448 threads and 4 threads per cell. But on a newer P100 on our university cluster, the block size is cut in half, and it's actually 16 threads per cell. And tuning this by hand is like an impossible challenge. And so we use periodic runtime auto-tuning. So we have this thin wrapper that we use around any kernel launch, where we use a CUDA event timing to measure how long the kernel launch took. And we feed in a parameter, a launch parameter that we scan through. And so we periodically do this in the simulations, and we only end up running a very small fraction of the time at non-optimal run parameters. And so this lets us both adapt to the simulation and dynamically choose the best parameters. Finally, so MPCD has a stochastic nature. I mentioned choosing random rotation vectors. And doing this on the GPU can be a bit of a tricky operation, especially because GPUs favor doing work and not loading data. And so loading something like a state of a random number generator can actually be fairly expensive if you need to do it per thread. And so we use a different strategy that's used in HUMD, where we first randomly generate a state for our random number generator using a cryptographic hash for every thread and every kernel launch. And then we generate microstreams of random numbers. So schematically, what that looks like is that if I want to draw a rotation vector for a cell, I feed in 3 parameters. One is the cell index of that cell, which is basically a per thread parameter, so every cell is unique. I feed in the time step, so that every time I do this operation, it's going to be another unique number. And then also a user-defined seed, which lets me randomize this between runs. We pass it through. We use the SARU random number generator, which uses a cryptographic hash. It's been shown to pass a battery of tests for uniform random numbers. And then I can use this then to draw a handful of random numbers that I need in a microstream. And so this is very effective because I'm getting a good instruction to load ratio from doing this. And on top of it, because I'm able to uniquely generate a random number state for each cell, I have no communication of random numbers required between different ranks. You could imagine that if different ranks drew numbers at the wrong time, then you would have different random numbers that you need to synchronize. We eliminate that, and that is a nice performance boost as well. OK, so finally, the numbers. What was all the point of doing all this work? So we did strong scaling tests for a 200 cube and a 400 cube box, so 80 million and 640 million particles. We first benchmarked on the CPU nodes. So we do have a CPU implementation as well that we've optimized, but not as heavily as the GPU one. We do get very good strong scaling performance out of that, running with on the Xe nodes with 16 processes on a node. For the GPU nodes, which are these solid symbols here, and again, this is time steps per second versus number of nodes. For the GPU nodes, we see that we have pretty good scaling up until large node counts, where we do see some decrease in efficiency. Overall, we get about a 3x speed up of our GPU code versus our CPU code, which we're very happy about. And this is also running only one process per XK node because there's only one GPU. If we had more than one GPU in a node, say in a future architecture, then we would be able to get much better node-to-node performance, head-to-head performance. I'll also note, although we didn't do an intensive strong scaling test, we do have pretty good, or extensive weak scaling test, we do have pretty good weak scaling as we go up, say, in 8 times the system size and 8 times the processors. We're covering basically the same performance. We did do some more direct profiling of the GPU runs to try to figure out what was bottlenecking us. And at high node counts, we found that it is our cell-to-cell communication. And it's really just our data that's in flight during that. And so moving forward, we're going to try 2 optimizations to improve that. One is to overlap some of that communication with our inner computations, which is very important for GPU codes. And also to test a mixed precision model, where we've done all these benchmarks in double precision so far. If we could reduce the amount of data we're transferring and by switching to some single precision, then we might be able to improve the performance there. But we need to test that to make sure that we have the right physics of energy and momentum conservation. And moving forward from there, then we'll be all set with a very nicely tuned code moving forward to do our scientific application, which was to study complex fluids in confinement. So that's what is headed down the road for me. I'd like to just mention one more time that our code is available online. It's in kind of a development state right now. It'll be in a tagged release of HUMD in the not so near, but not so far future. I'd like to thank the Blue Waters Project for the funding and support during the last year, and my point of contact, Jhook, who was great help as we took our adventures in Python on Blue Waters. This work was also funded by an NSF MRSEC at Princeton. And I'd like to thank NVIDIA, who's given us access to their PSG test cluster to try out, test the code on different GPU architectures. Thank you for your attention, and I'd be happy to take any other questions you have.